Sometimes in calculus we need to look not only the trend coming from both directions, but maybe we need to look at the trend coming from one direction and not the other. For example, in this blue curve here, what is happening? What's the limit as I get close to this endpoint here? Well, obviously I can't take the limit from both directions, or the trend from both directions, because there's nothing over here. Or what if you have a function that doesn't match up somewhere? How do you measure the trend coming to that gap from each direction? So we need to augment our definition of the limit to include that possibility. So what we'll do here is we'll suppose f of x is a function defined for x near a, and maybe f of a is not defined, that's okay. But the limit of f of x as x approaches a, and let's put in here a little point. And here we're going to say from the left. So here I'm going to have a limit as x approaches a from the left is L, and it's denoted like this. The limit as x approaches a, we'll put a little minus sign in the superscript of a, that means approaching a from the left, of f of x is L. If f of x gets arbitrarily close to L, as x gets arbitrarily close to a, this time not from either direction, but for x values less than a. So what this means on the picture is as I'm getting closer to a just from this one direction, what is my height doing from that one direction? Okay, so it's just the limit concept, except you're not having to approach from both directions this time. Your table only has to have one column, not two. And so we're just considering what's going on from that direction. Now, we can easily flip this around to get the other direction. So how do you do that? So I can say the limit of f of x as x approaches a, let's put in a different note, we'll write this one in pink, from the right, this time, is the limit as x approaches a, the limit of f of x as x approaches a, put a plus there, that means from the right, equals L. If f of x gets arbitrarily close to L, as x gets arbitrarily close to a, this time not for x less than a, but for x greater than a. And so from the right, it's just like what we're saying. The trend this time is not from less than a, it's coming from greater than a. As you get closer to a from the right side, what are your function values approaching from that perspective as well? Okay, so you can have a left-hand and a right-hand limit. Hopefully these match up. If they do, that's good. If they don't, well, we can still analyze what's going on. Now that we've shown the definitions of the left and right-hand limits, and we see that they are related to the limit, actually it's a little bit deeper than that. We can actually make a theorem here that can say that the limit as x approaches a of f of x equals L if and only if the limit as x approaches a from the left is L and the limit as x approaches a from the right is L as well. So the only way the limit's going to exist if the left and right limits equal each other. So as an example, we could have maybe a function that's something like x minus 1 for x less than or equal to 0, and how about x squared for x greater than 0. As a graph, we can quickly graph this. X minus 1 is something like this, and then at 0 you jump up to this quadratic, and you can see here that if I come from the left, I'm approaching -1. I'm coming from the right, I'm approaching 0. So since here the limit as x approaches 0 from the left of f of x equals -1, and the limit as x approaches 0 from the right equals 0, we can see then that the limit as x approaches 0 of f of x does not exist. Now another example, so these piecewise functions kind of make us weary at first, but they're not always in a position where they don't match up. For example, if I take the function sine x for x less than pi over 2 and 2 over pi times x, for x greater than or equal to pi over 2. This function looks something like this. So the sine function goes something like this. It hits 1 at pi over 2, at 0 at 0, and then it goes down to -1 and keeps bouncing back and forth, kind of like that. And then this 2 pi over x is just a line that passes through the point pi over 2, 1. So it's actually like this. Okay, so we can see here in this case, that as I'm coming from the left towards pi over 2, I'm approaching 1. As I'm coming from the right on towards 2 pi over 2, I'm at 2 pi over x. On the portion 2 pi over x, we approach 1. So here, this time, the limit as x approaches pi over 2 from the left of f of x equals 1, and the limit as x approaches pi over 2 from the right of f of x equals 1. Therefore, by our theorem, the limit does exist at pi over 2, and it is 1. Okay, now we want to look at an example of limits using a graph and see if we can match the definition of the limit with the graph. Alright, so I have this funny looking function, and it doesn't matter that it's ugly here, it just serves as an illustration. And first I want to know the limit as x approaches -3 from the right. Now remember what that means is so find -3, which is right here, x equals -3. And as I'm approaching -3 from the right hand side, what is the height of this thing doing? So if you notice, the height looks like it's going down to -2. So the limit -3 from the right is -2. If I look at -1 from the left, so here's x equals -1. As I'm writing this way towards -1, what's the height approaching? The height here looks like it's approaching +2. Okay, if I do -1 from the right, the limit as x approaches -1 from the right, that means I'm going this way towards x equals -1. So that would put me up here. As I'm getting closer to -1, my height value looks like it's going to +3. So the left hand and the right hand limit don't match up, so then we know that the limit itself does not exist. Okay, so the limit as x approaches -1 does not exist. Let's try 1. 1 from the left means I'm getting closer to x equals 1 over here. I'm going this direction. So the limit as x approaches 1 from the left would be 3. And coming to 1 from the right, as I'm getting closer this way, that means I'm kind of writing down this guy. That would put me at -2, right? As I get closer to x equals +1, coming from the right direction, I'm dropping down to 2. So that means, again, the limit as x approaches 1, the two pieces are not aligning, and so that means the limit here does not exist. And I also want to point out that sometimes the limit could exist, but your function value may be different. So for example, here the limit doesn't exist, but the function value at 1 is the value 1. So the solid dot tells you where your function value is. Alright, now if I move on to 3 from the left, so here's 3, as I'm going this direction, I'm going up this slide, I would end up at 2. And coming from the right, which is the bigger side, alright, so I'm coming this direction, I'm approaching 2 as well. This time the two pieces do match up, so the limit as x approaches 3 is going to be +2. Okay, now I want to point out this last one here. The limit as x approaches 2, so I'm doing both directions here. Where is x equals 2? Right here? Well, I don't have any big dots or any jumps like that, so how do I evaluate this? Well, you have to imagine that just because I don't draw a dot doesn't mean a dot's not there. That is the function value. It just looks smooth so we don't draw a bunch of dots and then connect the dots here. So as I'm getting closer to 2 from each direction, the heights are both approaching 0. So the limit will be 0 there. I hope these one-sided limits make sense. If you have any questions on them, please let me know. I'd be glad to go over more examples if needed. And just thanks for watching.